Sampling tool. Here the continuous sampling tool means it is a tool which is used to convert the continuous signal using analog to is converted into or is sampled using analog to digital converter, and this device with various physical limitations. So the result in derivations from the theoretically perfect reconstruction collectively referred to as a distortion. ADC tool is used for conversion. So after sampling, our signal is not yet completely digital because the values x of n can still take on any number from a continuous range. So we use the term like discrete time signal. Suppose input signal x of t is a cos of omega t plus phi, and x of n is x of n ts. So the equation will be a cos of omega n ts plus phi, that is a cos of omega n plus phi. Analog signal is sampled every ts second. So ts is what? Ts is nothing but the sampling interval. Fs is what? Fs is 1 by ts, that is sampling rate or sampling frequency. Basically there are three sampling methods. One is ideal, second one is natural, and third one is flat top. So ideal means here an impulse at each sampling instant. Natural means here a pulse of short width with varying amplitude, and flat top means here sample and hold like natural but with single amplitude value. The process is referred to as pulse amplitude modulation, that is PM, and the outcome is a signal with analog values. So there are three sampling methods: ideal, natural, flat top. In ideal, impulse at each sampling instant, natural with varying amplitude, and flat top means sample and hold. Now these three different sampling methods. First one is the ideal sampling, that is here impulse at each sampling instant, that is impulse at each sampling instant. The second one is natural sampling, here a pulse of short width with varying amplitude, and the third one is flat top sampling. So this diagram is ideal sampling and impulse at each sampling instant, which is shown in the previous figure. Now the reconstruction. Now what is reconstruction? It is nothing but getting the original signal without any loss. So reconstruction is the process of creating an analog voltage or current or the analog signal from the sample. A digital to analog converter takes a series of binary number and it recreates the voltage or current levels that correspond to the binary number. Then this signal is filtered by low pass filter. So reconstruction means it is a process of creating again an analog signal from the samples. For that, a digital to analog converter is used. Now the next concept is aliasing. So aliasing can be referred to as a phenomenon of high frequency component in the spectrum of signal. So aliasing can be the phenomenon of high frequency component in the spectrum of signal taking an identity of low frequency component in the spectrum of its version. The corrective measure taken to reduce the effect of aliasing. In the transmitter section, low pass anti-aliasing filter is used before the sampler to eliminate the high frequency component, and these high frequency components are unwanted, so we have to remove it. The signal which is sampled after filtering is sampled at a rate slightly higher than the Nyquist rate. This choice of having a sampling rate higher than the Nyquist rate also helps in easier design of reconstruction filter at receiver. So the time limited signals cannot be band limited. Since all the signals are more or less time limited, they cannot be band limited. Therefore, we must use a low pass filter on most of the signals before sampling. This is called as anti-aliasing filter, and these are typically built into an analog to digital converter. If the signal is not band limited, distortion will occur when the signal is sampled. So we refer to this distortion as aliasing. If signal is not band limited, distortion occur, and when the signal is sampled, so we referred as a aliasing. Sampling and digital signal processing can be combined to create high performance sampler. For example, CD player use an oversampling approach which involves sampling the signal at a very high rate and then downsampling it to avoid the need to build high precision converter and filter. So reconstruction using just the samples x of n equal to x of n ts to return to the original continuous time signal x of t. Ideal reconstruction refers to the exact reconstruction of x of t from its sample as long as the sampling theorem is satisfied. So in some extreme case example, this means that sinusoidal having a frequency just less than fs by 2, it can be reconstructed from the samples taken at rate f of s. So simply D to C converter, that is discrete to continuous converter, perform the interpolation on the sample value y as they are placed on the time axis. Two very simple interpolation functions are zero order hold and linear interpolation. With zero order hold, each sample value is represented as rectangular pulse of width ts and height yn. With linear interpolation, the continuous waveform values between each sample values are performed by connecting a line. But both these cases introduce errors, so we have to use a better must exist, that is a complete sampling and reconstruction system require both C to D and D to C converters. The next is continuous time versus discrete time. Continuous time system, it is good for analogous and general understanding, appropriate mostly to analog electronic system, that is x of t is given to one system, then y of t is the output. The electronics are increasingly digital, so we use digital ASIC chips FPGA microprocessor to implement the system and to process the signals. Signals are converted to the numbers, processed and converted back. So if x of t, that is continuous signal, is input, that is analog input, it is given to A to D converter, that is analog to digital converter. Then the output of this is x of n, and then it is given to the computer, or we can say it is given to one system. Output of this computer or a system is y of n. It is again given to the D to A converter, that is digital to analog converter. Then output of this system is again y of t, that is in the analog form. Next is signal space concept or vector concepts. The key to analyzing and understanding the performance of digital transmission is the realization that signals used in the communication can be expressed and visualized graphically. Vectors and space. Consider an n-dimensional space with unity basis vectors, that is vector means e1 e2 dot 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 en. Any vector a in the space can be written as, vector can be written as, or it can be represented by a equal to summation I to I equal to 1 to n a I e I, where value of a varies from a1 a2 dot 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 n a n. What is n? It is nothing but the dimension, that is minimum number of vectors that is necessary and sufficient for the representation of any vector in the space. So consider n dimensional space having a vectors e1 e2, and any vector in the space can be written by using this equation. Next, linear vector spaces. In order to facilitate the geometrical representation of the signal, we treat them as a vector. So what is vector? To facilitate the geometric representation of the signal, we consider these as a vectors. We treat them as a vectors. Indeed, the signals can be considered like a vectors as will shown in the sequence. For that purpose, we recall the properties. For that, we have to see the properties of linear vector spaces. The linear vector space is called a linear vector space if it satisfies the following conditions. It is called a linear vector space if it satisfies following conditions. So what is the first condition? If x plus y is equal to y plus x. The second condition is x plus y plus z is equal to, in bracket, x plus y plus z. The third condition is a of x plus y is equal to ax plus ay. The fourth condition is alpha plus beta of x is equal to ax plus beta x. Now what is x and y? Then x and y are arbitrary vectors. And what is alpha and beta? Alpha and beta are the scalars. So for what purpose vectors are used? For the geometrical representation of the signal. And vector space, linear vector space have to satisfy follow these four conditions, where x and y are the arbitrary vectors and alpha and beta are scalars. Next is orthogonality. In mathematics, orthogonal functions belong to the function space, which is a vector space. So when the function space has an interval as the domain, then integral of the product of the function over the interval is given by this equation. So before we move to the next point, eigenvector, we will see the advantages of digital transmission. What are the advantages? It has a noise immunity, error detection and correction, ease of multiplexing, integration of analog and digital data, use of signal regenerators, data integrity and security, ease of evaluation and measurement, and it is more suitable for the processing. These all are the advantages. And what are the disadvantages? The first disadvantage is more bandwidth required. The next one is need of precise time synchronization. The third one is additional hardware for encoding and decoding, integration of analog and digital data, sudden degradation, and the last one is incompatible with existing analog facilities. So we develop a geometric representation of the signal waveform as a points in a signal space. Such a representation provides a compact characterization of the signal set for transmitting information over a channel and simplifies the analysis of their performance. So we use a vector representation which allows to represent waveform communication channels by a vector channels. suppose we have a set of m signal waveform, so and we want to use this waveform to transmit over a communication channel. Then we find a set of m greater than or equal to n, that is orthonormal basis waveform for our signal space, from which we can construct all of our m signal waveforms. Orthonormal in this case implies that the set of basis signals are orthogonal. So we represent each signal waveform by its vector coefficient, knowing that what the basis functions are to which they correspond. So we similarly think of the point in n-dimensional space. Next is eigenvector. In linear algebra, an eigenvector or the characteristic vector of square matrix is a vector which does not change its direction under associated linear transformation. In other words, if V is a vector which is not zero, then it is eigenvector of square matrix A. If AV is a scalar multiple of V, this condition should be written as the equation AV equal to lambda V. The eigenvectors x and the eigenvalues lambda of the matrix A satisfies Ax equal to lambda x. If A is n by n matrix, then x is n cross n cross 1 vector and lambda is a constant. The equation can be rewritten as A minus lambda I of x equal to 0, where I is identity matrix having n by n. Now computing the eigenvalues. Since x is required to be non-zero, the eigenvalues must satisfy determinant of A minus lambda I of 0, which is called the characteristic equation. Solving it for the values of lambda, which gives the eigenvalues of matrix A. So the equation for a characteristic equation is written as determinant of A minus lambda I equal to 0. This is characteristic equation. Eigenvalue. So lambda is a scalar which is known as an eigenvalue or a characteristic value which is associated with eigenvector V. So eigenvector is denoted by V and eigenvalue is denoted by lambda, and it is a scalar value. So we can find the eigenvalues by determining the roots of the characteristic equation with A minus lambda I equal to 0. So let us see one example. If A is n by n matrix, is there exists a non-zero vector x in R of n such that Ax is a scalar multiple of x. Now what is A? A is n by n matrix, lambda is scalar and x is non-zero vector. So this diagram shows the geometrical interpretation. Let A be n by n matrix with eigenvalue lambda and corresponding eigenvector x. So Ax equal to lambda x. This equation can be Ax minus lambda x equal to 0, given that A minus lambda in of x equal to 0. So we are solving this equation A minus lambda in equal to 0, where lambda leads to the all the eigenvalues of A. On expanding the determinant A minus lambda in, we get a polynomial in lambda. This polynomial is called characteristic polynomial of A. The equation A minus lambda im equal to 0 is called the characteristic equation of A. Let us see one example. Now here verifying the eigenvalues and eigenvectors. There is a one matrix A having values 2 0 0 minus 1. X1 is 1 by 1 of 0, x2 is 0 1. Now first A of x, that is multiplication of matrix A and matrix x1, which is equal to, output of this is, this two matrix multiplication is 2 0. Now here 2 is taken as a common from the matrix, so next is 2 in matrix 1 and 0. So here 2 is the eigenvalue and matrix 1 0 is eigenvector, that is 2 of x1. Now similarly ax2, that is multiplication of matrix A and matrix x2, output of this is 0 minus 1. Minus 1 is taken as outside, so here eigenvalue is minus 1 and eigenvector is 0 1. Next is finding the characteristic equation, finding the eigenvalues, eigenvectors, characteristic equation. So matrix A having value 2 1 minus 12 minus 5. So for characteristic equation is lambda I minus A, which is determinant. So lambda value is lambda minus 2, 12 minus 1, lambda plus 5. So we solve this equation and we get lambda, value of lambda as minus 1 minus 2. So these are two eigenvalues, that is lambda is equal to minus 1 minus 2 is eigenvalue. So eigenvalues are lambda 1 and lambda 2 having values lambda 1 equal to minus 1, lambda 2 is equal to minus 2. So the next is keeping these lambda values in the matrix and we get these values, that is lambda 1 I minus A of x, and we solve this matrix, we get the final value. Similarly we will put lambda 2 is equal to minus 2 and we solve the matrix. In this way we get eigenvalues and eigenvectors. Now the DSP system and the algorithms are used for managing and manipulating the streams of the data, and therefore it requires high precision and timing accuracy. A digital filtering algorithm can be used to remove unwanted frequencies from a data stream. Similar mathematical algorithms can be used for a signal analysis and audio-video manipulation and data compression for communication. A DSP system communicates with external world through analog to digital converter and digital to analog converter. So analog elements of the system also require a careful design. So this is the basic block diagram of DSP. It has input as an analog signal given to analog to digital converter. Output of ADC is digital signal which is given to the digital signal processor, that is DSP. Output of DSP is digital signal which is given to again digital to analog converter, that is DAC, and output of DAC is analog signal. So ADC, what is the role of ADC? It convert analog signal to digital signal. What is the role of DSP? It perform the amplification, attenuation, filtration, spectral analysis, feature extraction, etc. operation on digital data. So this is our main part of the system. So DAC, again it is nothing but the digital to analog converter. So some process signals are required back in the analog form. For that purpose DAC is used and it converts the digital output to its analog equivalent. Next is discrete time signal. So discrete time signals are defined as discrete time instant and between. So discrete time signals are defined as a discrete time instant and between the two discrete time instants which are not zero, but it can be obtained either by sampling analog signal or it can be a discrete in nature like discrete measurement signals. A discrete time signal having a set of discrete values and it is a digital signal. So the sampling and analog signal produces the discrete time signals and the quantization of its values produces a digital signal. So the sequence of the values x of 0 to x of n minus 1, it may be considered as the elements of column vector as given. The last one is comparison between the digital and analog signal processing. We already know that the digital signal processing is more versatile, analog signal processing is less versatile. Digital signal processing, it has a more repeatability, analog signal has less repeatability. Digital signal processing have more accuracy as compared to analog. Digital signals can be easily stored, but analog signals are difficult to store. Mathematical processing algorithm can be easily implemented in digital signal processing, and in analog it is difficult to implement. In digital, the upgradation can be done easily, but in analog upgradation is difficult. In digital signal processing, universal compatibility is possible. Here it is not possible in analog. But there are two disadvantages that is of digital, that is more here the system complexity is more, but in analog the system complexity is less. In digital there is more power consumption required, and in analog less power consumption is required. Thank you.